High above the Earth right now, a satellite is quietly correcting one of its own clocks, not because anything is broken, but because up there, a little further from the pull of our planet, time itself moves at a very slightly different pace than it does for us on the ground. It is a tiny difference. Left uncorrected, it would take centuries to become obvious to the naked eye, but engineers have to account for it every single day, or the whole system would slowly drift out of step with the world below. It is a strange thing to sit with. Time, the thing we usually think of as the steadiest measure there is, turns out to bend depending on where you are standing and how strongly gravity is holding onto you there. This idea sits at the heart of one of the most far-reaching shifts in the history of science, and it did not come easily. For more than 2 centuries, gravity was understood the way Isaac Newton had described it in the late 1600s, a force of attraction between any two objects with mass, growing stronger the closer they are and the more massive they are, weakening steadily with distance. Newton's version of gravity worked. It let astronomers predict the motion of planets with remarkable precision, and it powered centuries of engineering, from bridges to orbital trajectories, but it left an odd, quiet question sitting underneath all of it. How does gravity actually reach across empty space? If the sun vanished this instant, how would the Earth know to stop curving around it? Newton's equations could tell you exactly how strong the pull was, but they could not explain how that pull crossed the emptiness between two bodies with nothing to carry it. It took until the early 20th century for someone to offer a genuinely different way of thinking about the problem, and it came from a young physicist named Albert Einstein. His answer was not an improvement to Newton's force. It was a replacement of the entire picture. Einstein proposed that gravity is not a force reaching out across space at all. Instead, it is a consequence of geometry. Mass and energy bend the shape of space and time around them, and objects moving through that bent landscape simply follow the straightest path available, a path that, from our point of view, looks curved. A planet orbiting a star is not being pulled by an invisible string. It is coasting along a curved valley in the fabric of space and time, a valley carved into existence by the star's own mass. To arrive at this, Einstein leaned on a simple observation that quietly unsettles anyone who thinks about it for long enough. Imagine you are standing in a windowless room with no way to look outside. If you feel your feet pressed to the floor, there are only 2 possible explanations. Either the room is sitting still on the surface of a planet and what you feel is ordinary gravity, or the room is out in empty space, far from any planet, being accelerated upward at a steady rate by some engine beneath it. From inside the room, with no windows, there is absolutely no experiment you could run that would tell you which situation you were in. Gravity, in other words, is not obviously distinguishable from acceleration. Einstein called this the equivalence principle, and he treated it not as a curious coincidence, but as a deep clue about the true nature of gravity. If acceleration and gravity felt identical from the inside, then perhaps gravity was not a separate ingredient of the universe at all, but simply what acceleration looks like when it is caused by the curvature of space and time itself. Working through the mathematical consequences of this idea took Einstein the better part of a decade, developing what would eventually be published as the general theory of relativity in 1915. The theory made several predictions that had no place at all in Newton's older picture. Light, which has no mass, should still be bent by the gravity of a massive object because it too follows the curved geometry of space, not because gravity pulls on it directly, But because the space it travels through is itself warped, time should run at different rates, in different gravitational strengths, ticking more slowly deeper in a gravitational well, and the orbit of a planet very close to a strong source of gravity should drift very slightly out of its expected path in a way Newton's equations could never fully account for. That last prediction turned out to matter immediately because astronomers already had a small, nagging puzzle sitting on their desks. Mercury, the innermost planet, has an elliptical orbit, and the point in that orbit where it comes closest to the Sun slowly rotates around the Sun over time, a behavior known as precession. Newton's gravity could explain most of this drift as the gravitational tug of the other planets, but a small remainder, only a few dozen seconds of arc per century, stubbornly refused to be explained. It was a tiny discrepancy, easy to imagine explaining away with some undiscovered planet or unseen dust. In fact, one had already been proposed and given a name, Vulcan, a hypothetical world orbiting even closer to the Sun than Mercury, invoked purely to tug Mercury's orbit into line. No such planet was ever found, because none exists. When Einstein applied general relativity to Mercury's orbit, the curvature of space and time near the Sun accounted for the missing precession almost exactly, without needing any new planet at all. It was one of the first hints that this strange geometric picture of gravity was not just elegant, but true. The far more dramatic test came 4 years later, in 1919, during a total solar eclipse. If light bends around a massive object the way general relativity predicted, then stars positioned just behind the Sun, ordinarily invisible in its glare, should appear to shift slightly out of position during an eclipse. Their light bent around the Sun's edge on its way to Earth. 2 expeditions, one to the island of Príncipe off the coast of West Africa, and another to Sobral in Brazil, photographed the stars near the darkened Sun and compared their positions to photographs taken months earlier, when the same patch of sky was visible at night without the Sun anywhere near it. The stars had indeed shifted, and by almost exactly the amount Einstein's equations predicted, twice what Newton's older theory would have suggested if light bent at all. The announcement made headlines around the world. A quiet German physicist working in Berlin had just shown that the shape of the universe itself was not what anyone had assumed. Once the curvature of space and time was accepted as real, the question of time dilation stopped being a footnote and became something worth testing directly. If gravity is curvature, and moving through curved space-time changes how time flows, then clocks sitting at different distances from a massive object should genuinely tick at different rates, not just as some abstract mathematical bookkeeping trick, but as something you could, in principle, measure with real instruments. The first clean laboratory demonstration of gravitational time dilation came in 1959 in the basement and attic of a physics building at Harvard University in an experiment carried out by Robert Pound and his student Glenn Rebka. Their setup was elegant in its simplicity. They took a source of gamma radiation, a very high-energy form of light, and placed it at the top of a tower roughly 22 meters tall. At the bottom, they placed a detector tuned to absorb that exact frequency of gamma rays. According to general relativity, as the light fell from the top of the tower to the bottom, moving slightly deeper into the Earth's gravitational well, its frequency should shift upward by an almost unimaginably small amount, gaining energy the way a ball gains speed as it falls. Pound and Rebka detected exactly that shift, confirming Einstein's prediction to within about 10%, a result the same team refined several years later to within about 1%. It remains one of the most precise confirmations of general relativity ever performed, and it firmly moved gravitational time dilation out of the realm of theory and into the realm of measured fact. A more intuitive version of the same idea came a little over a decade later, in 1971, when physicists Joseph Hafele and Richard Keating took 4 extremely precise atomic clocks and flew them around the world on commercial airliners, first eastward and then westward, while an identical set of clocks stayed behind on the ground. When the traveling clocks were brought back and compared to the stationary ones, they had drifted out of sync, and the size and direction of that drift matched what relativity predicted. Once both gravitational time dilation and time dilation caused by their motion through space were accounted for together. It sounds almost too strange to be real, clocks disagreeing with each other simply because one of them went on an airplane trip, but the numbers lined up. Time is not the fixed, universal backdrop it feels like from inside an ordinary life. It is something that responds, in small but entirely real ways, to speed and to gravity. These effects are not confined to laboratories and curious experiments. They matter for technology that many people rely on every single day. Global positioning satellites orbit the Earth at an altitude of roughly 20,000 kilometers, far enough out that the planet's gravity is noticeably weaker than it is at the surface, and fast enough in their orbits that a second kind of time dilation, caused by their speed, comes into play as well. The two effects push in opposite directions. Being farther from Earth's gravity makes the satellite's clocks run faster than clocks on the ground. Moving quickly through space makes them run slower. When the numbers are added together, the net result is that clocks aboard positioning satellites gain about 38 microseconds every day compared to clocks on the surface. That sounds negligible, a few dozen millionths of a second, but the positioning system calculates location based on the precise timing of signals traveling at the speed of light, and at that speed, 38 microseconds of drift per day would translate into a position error that grows by roughly 10 kilometers every single day if left uncorrected. Engineers built the correction directly into the system from the start, adjusting the satellite's onboard clocks before launch, so that once they reach orbit and experience both effects, they naturally settle into agreement with clocks on the ground. It is a strange thought that the phone in someone's pocket, quietly finding its location on a map, is only able to do so because of a correction rooted in general relativity. Given how real and measurable this effect is, it is worth asking just how significant it becomes in more extreme settings. On the surface of the Earth, gravity is comparatively gentle, and the resulting time dilation, while real and technologically important, amounts to only a handful of seconds of difference across an entire human lifetime compared to a hypothetical location with no gravity at all. The Sun, despite being roughly 330,000 times more massive than the Earth, still is not massive or dense enough at the distance we orbit it to produce more than a similarly modest effect on the order of a few tens of seconds across a lifetime. Even standing on Mercury, the planet that swings closest to the Sun of any in our solar system, would only shift that number by another few seconds. An interesting curiosity, but nowhere near enough to meaningfully lengthen anyone's life, even setting aside the fact that Mercury has virtually no atmosphere and daytime temperatures hot enough to melt certain metals. The Sun would need to be millions of times more massive than it actually is before the time dilation near it became large enough to notice without extremely sensitive instruments. So if ordinary stars barely move the needle The natural next question is, what kind of object would, and here the answer becomes genuinely dramatic. At the centers of most galaxies, including our own, sit objects called supermassive black holes, with masses ranging from roughly 1,000,000 to several billion times the mass of the Sun, compressed into a region of space with no surface at all in the ordinary sense, just a boundary called an event horizon beyond which nothing, not even light, can escape. Falling toward an object like this, time dilation stops being a subtle correction and becomes overwhelming. Close enough to the boundary of a supermassive black hole, an outside observer watching through a telescope would see your clock ticking slower and slower, your movements stretching out, your very breathing appearing to take longer and longer to complete, approaching a dead stop as you neared the horizon, even though from your own perspective, nothing about your experience of time would feel unusual at all. You would still feel every second pass normally. It is the person watching from far away whose perception of you changes. In principle, someone could spend what felt to them like a single afternoon skimming close to such an object and then pulling away, only to return and find that centuries had passed for everyone they had left behind. What happens if you cross that boundary rather than turning back is a question general relativity cannot fully answer, at least not on its own. The equations that describe the region right at the edge of a black hole, and certainly the region beyond it, push the theory to its limits, predicting a point at the very center called a singularity, where the mathematics simply breaks down and stops producing meaningful answers. Physicists broadly suspect that describing what actually happens there will require merging general relativity with quantum mechanics, the other great pillar of modern physics, into some deeper theory that does not yet exist in a form everyone agrees on. It remains one of the most active open problems in all of physics, and it is worth sitting with for a moment. A theory good enough to correct the clocks in every phone on the planet still cannot tell us, with certainty, what lies at the heart of the very objects it also predicts. Gravity is not the only way to push time dilation to an extreme, and it is worth being clear about the difference, since the two mechanisms are related but distinct. Gravitational time dilation, the kind described so far, comes from general relativity and depends on how deep an object sits within a gravitational well. A second, separate kind of time dilation comes from special relativity, the somewhat simpler theory Einstein published a decade before general relativity, and depends purely on how fast an object is moving relative to an observer, with no gravity required at all. The Hafele-Keating airplane clocks, mentioned earlier, actually experienced a mix of both effects at once, since flying at altitude changes both an object's speed and its distance from the Earth's gravity, and untangling the two contributions was part of what made that experiment such a careful piece of analysis. Taken to its own extreme, velocity-based time dilation produces a scenario often called the twin paradox. Imagine one twin stays on Earth while the other boards a spacecraft capable of traveling at a large fraction of the speed of light, journeys to a distant star, and then returns. From the perspective of the twin who stayed home, the traveling twin's clock runs slow for the entire outward and return trip, so that when the traveler finally steps off the spacecraft, less time has passed for them than for the twin who never left. An age difference that grows larger the closer the ship's speed gets to the speed of light itself. It is called a paradox, mostly out of habit rather than because it contains any actual contradiction, since a naive reading might suggest that, by symmetry, each twin should see the other as the one who aged less. The asymmetry that resolves this is that only the traveling twin undergoes acceleration, speeding up to leave, turning around at the distant star, and slowing down to return, while the twin who stays on Earth experiences no such acceleration at all. And it is this asymmetry, not merely relative motion, that breaks the tie and picks out the traveling twin as the one who genuinely ages less. Pushed to its absolute limit, an object moving at the speed of light itself, something only massless particles, like photons, can actually do, would experience no passage of time whatsoever between departure and arrival, however long that journey appeared to take. From the perspective of everyone left behind, a strange but mathematically consistent consequence of the same equations. This is not merely a thought experiment confined to chalkboards. One of the cleanest everyday confirmations of velocity-based time dilation comes from particles called muons, created when cosmic rays from deep space strike the upper atmosphere many kilometers above the Earth's surface. Muons are unstable, decaying into other particles after an average lifetime of only a couple of millionths of a second, far too short by any ordinary calculation for them to survive the trip down through the atmosphere to reach a detector on the ground, even traveling close to the speed of light. And yet, they do reach the ground in large numbers and have been detected doing so since the middle of the 20th century. From the muon's own point of view, the discrepancy resolves painlessly because at such extreme speed, the muon experiences the thickness of the atmosphere as considerably shorter than we would measure it to be, a companion effect to time dilation called length contraction. So there is simply less distance left to travel before it decays. From the perspective of an observer standing on the ground, the resolution instead comes from time dilation directly, since the rapidly moving muon's internal decay clock runs slow relative to ours, giving it enough extra time, from our point of view, to complete the journey before decaying. Both descriptions, one framed around a shortened distance and the other around a slowed clock, agree completely on the observable outcome: muons reaching the ground in numbers that would be impossible without some form of relativistic effect at play. And this quiet, continuous shower of surviving muons has served as one of the most accessible, ongoing confirmations of special relativity for decades. In practice, human-built spacecraft remain nowhere near fast enough for this kind of effect to matter much. Even the fastest object ever built by humans, a solar research spacecraft that has passed repeatedly through close approaches to the Sun, reaches speeds of a few hundred kilometers per second at its fastest, only a small fraction of 1% of the speed of light, producing a velocity-based time dilation too small to matter for any practical purpose, though not literally zero, and in principle measurable with sufficiently sensitive instruments. It is really only within particle accelerators, where subatomic particles are routinely pushed to more than 99% of light speed, and within the natural cosmic ray showers producing muons in the atmosphere above us, that velocity-based time dilation becomes large enough on Earth to observe directly and routinely, standing as a everyday, essentially invisible reminder that the twin paradox is not merely a philosophical curiosity, but a measured feature of how the universe actually behaves. Zooming out from the extreme, tight curvature around a black hole, gravity also shapes the universe on the largest scales imaginable. And one of the stranger discoveries of the last century is that we, along with our entire galaxy, are quietly being carried through space by forces we only partly understand. To appreciate how strange this is, it helps to go back to a moment when astronomers did not even know that other galaxies existed. For a long stretch of the early 20th century, the common assumption was that the Milky Way made up essentially the entire universe, and that the faint, fuzzy smudges of light visible in telescopes, smudges we now know to be distant galaxies, were simply clouds of gas drifting somewhere within our own galactic neighborhood. That assumption held until 1924, when the astronomer Edwin Hubble, observing one of these smudges, known then as the Andromeda Nebula, identified a particular kind of star within it called a Cepheid variable. Cepheid variables brighten and dim in a very regular, predictable rhythm, and that rhythm happens to be tightly linked to how intrinsically bright the star actually is, a relationship discovered a decade earlier by the astronomer Henrietta Leavitt. By timing the star's pulse and comparing its true brightness to how faint it appeared from Earth, Hubble could calculate its distance with real precision. The number that came back was staggering, placing that single star, and therefore the entire Andromeda Nebula surrounding it, far outside the boundaries of the Milky Way entirely. What had looked like a nearby cloud of gas was in fact an entire galaxy in its own right, roughly comparable in size to our own, sitting an immense distance away. The universe had just become dramatically larger overnight, filled not with one galaxy, but with countless others waiting to be found. Once astronomers accepted that galaxies existed far beyond our own, a new project began almost immediately, mapping where all of them actually were. This turned out to be a much slower undertaking than anyone expected. By the 1970s, astronomers including Stephen Gregory, Laird Thompson, and William Tift had shown that galaxies do not scatter randomly through space. Instead, they cluster together into enormous structures, sheets and filaments of galaxies stretched across the sky, separated by vast, comparatively empty regions called voids. The first such structure to be carefully mapped, a grouping now called the Coma supercluster, spanned roughly 100 million light-years across, an almost incomprehensible scale. And yet, astronomers eventually found that around 95% of all galaxies live within structures like it, gathered into filaments, rather than spread evenly through space. The universe, on its grandest scale, looks less like a uniform mist of galaxies and more like a vast, three-dimensional web, with galaxies clustered along its strands and emptiness pooling in the gaps between them. Strangely, even though astronomers were mapping superclusters of galaxies hundreds of millions of light-years away, well before the end of the 20th century, it took until 2014 to fully map the supercluster containing our own galaxy, a structure eventually named Laniakea. Given that this is our own neighborhood, it seems backward that distant structures were understood before our local one, but the reason has to do with a simple, almost mundane obstacle. The Milky Way itself is full of gas and dust, and that material sits directly in the way of much of our view toward the center of our own galaxy and the regions beyond it. Astronomers call this obscured band of sky the zone of avoidance, because so little light manages to pass through it. Ironically, distant galaxies scattered across the rest of the sky are often easier to study than the structures closest to us, simply because most directions in the sky are not blocked by our own galaxy's dust, while a frustratingly large and important slice of the sky is. Mapping Laniakea required a different approach than simply plotting galaxy positions. Astronomers, led by a team including Brent Tully, instead tracked the peculiar motion of galaxies, meaning their movement relative to the smooth, overall expansion of the universe. The leftover drift caused by gravity pulling on them locally rather than the universe stretching uniformly in every direction. By carefully measuring these small deviations across thousands of galaxies, they could work backward to infer where the greatest concentrations of gravitational pull must be sitting, even in regions partly hidden behind the zone of avoidance. The resulting map revealed that our galaxy, along with everything else in Laniakea, sits within a vast basin of attraction, all of it slowly flowing toward a region roughly 150 to 250 million light-years away, known as the Great Attractor. That name sounds almost mythic, but the object itself is simply an especially dense concentration of galaxies and dark matter, one that happens to sit squarely within the zone of avoidance, making it frustratingly difficult to study directly even now. The story does not stop there, because Laniakea itself, the entire supercluster containing our galaxy, turns out to be drifting as a whole toward an even more distant concentration of mass called the Shapley supercluster, an enormous structure lying even farther away than the Great Attractor. When astronomers added up all the visible and inferred mass sitting in that direction, though, they ran into a shortfall. There simply was not enough mass in the Shapley supercluster, even accounting for the unseen dark matter astronomers already knew must be there from decades of work on galaxy rotation. Most famously, the observations of Vera Rubin in the 1970s, showing that galaxies spin far too quickly to hold together under the gravity of their visible matter alone. Even with dark matter added generously to the ledger, the pull from Shapley could only account for roughly half of our galaxy's observed motion. Something else, sitting somewhere else, had to be contributing the rest. The answer, proposed in 2017 by a team of researchers, including Yehuda Hoffman, Daniel Pomarede, Brent Tully, and Hélène Courtois, turned out to be almost the opposite of what anyone expected. Gravity, as far as anyone has ever observed, only pulls. It does not push. So when the team built a detailed map of the flow of galaxies around us and found that a significant share of our motion pointed away from a particular patch of sky rather than toward the Shapley supercluster, it looked, on the face of it, like something in that region was actively repelling us. They named the feature the dipole repeller, and for a moment, it invited genuinely exotic explanations. Some kind of undiscovered repulsive force, or even the theoretical opposite of a black hole, sometimes called a white hole, sitting there and pushing outward. The real explanation turned out to be quieter, and in its own way, more interesting. The dipole repeller is not a source of anything. It is an absence. It is a void, an enormous bubble of space, roughly 100 million light-years across, containing few galaxies and comparatively little mass of any kind, one of the emptier regions sitting between the filaments of the cosmic web described earlier. Nothing there is pushing anything. Instead, imagine a hypothetical galaxy sitting in a universe where matter is spread with perfect evenness in every direction. The gravitational pull from every direction would balance out exactly, leaving that galaxy with no net motion at all, held in a kind of gravitational equilibrium. Now remove the matter from just one direction, replacing it with a void. The pull from the opposite direction is no longer balanced by anything, so the galaxy begins to drift away from the empty region, not because the void pushed it, but because the pull it used to feel from that direction has simply gone missing. From the galaxy's point of view, and from ours, it looks exactly like being pushed, even though nothing but an absence of pulling is actually involved. There is a second, complementary reason voids seem to expand relative to their surroundings, tied to the universe's overall expansion. Space itself is stretching everywhere, but that stretching is resisted to varying degrees by gravity. In regions dense with galaxies, mutual gravitational attraction holds matter together and slows the local rate of expansion. In a void, with almost nothing there to resist it, the underlying expansion of space proceeds largely unopposed, so the void swells faster than the denser regions around it. Both effects, the missing pull and the comparatively unchecked expansion, appear to work together, making regions near a void seem to be pushed away from it, even though the true cause, in both cases, is an absence of gravity's usual pull rather than any new force in the opposite direction. It is worth being honest about how solid this picture actually is, because the dipole repeller sits partly within the same dust-obscured zone of avoidance that makes the great attractor difficult to study, and because confirming a void means confirming an absence, proving that galaxies genuinely are not there rather than merely undetected, it remains a more tentative piece of the picture than the well-established structures like Laniakea itself. Researchers studying it have been candid that further, more sensitive surveys across multiple wavelengths of light will be needed to firmly confirm both its existence and how much it truly contributes to our galaxy's motion. For now, it stands as a compelling hypothesis, well supported by the flow patterns of galaxies around us, but still an area of active investigation rather than settled fact. There is a pleasing symmetry in all of this. The same theory that explains why satellites need their clocks corrected and why time would nearly stop for someone falling toward a black hole also explains why an entire galaxy can appear to be pushed by a region of space that, as far as anyone can tell, contains almost nothing at all. In every case, the underlying cause is the same one Einstein identified: mass curves, space and time, and everything else, from a satellite's clock to the sweeping motion of galaxies across hundreds of millions of light years, follows from how that curvature is arranged. It is worth pausing on a related point that sometimes causes confusion: the relationship between an object's size and how strong its gravity actually is. It might seem reasonable to assume that a bigger planet automatically means stronger gravity at its surface, but that turns out not to be true, because gravity at a surface depends not just on total mass, but on how tightly that mass is packed together, its density, and how far the surface sits from the center where the mass is concentrated. The Moon, for instance, has surface gravity only about 1/6 as strong as Earth's, and Pluto's is weaker still, at roughly 1/15. Uranus, meanwhile, has a radius about 4 times larger than Earth's, and yet its surface gravity comes out to only about 90% of Earth's, because Uranus is made largely of gas and ice, spread thin across an enormous volume. Saturn is an even more striking case, with a radius roughly 9 times that of Earth, but a surface gravity only about 8% stronger than our own, again because so much of its bulk is low-density gas. Jupiter, dense enough and massive enough to overcome its own large size, ends up with surface gravity around 2.5 times that of Earth, and the Sun, despite being made overwhelmingly of light hydrogen and helium, is so enormous that its immense size ultimately wins out over its comparatively modest density, giving its surface gravity almost 28 times stronger than Earth's. Mass matters, but so does how that mass is arranged, and the two factors do not always point in the same direction. This interplay between mass and distance is easiest to picture with a simple, well-worn classroom demonstration, the kind found in many physics classrooms. Stretch a flexible sheet of fabric tightly across a frame and place a heavy weight at its center. The sheet dips downward around the weight, forming a curved well. Roll a small marble along the sheet near the edge, and rather than moving in a straight line, it curves inward, circling the central weight for a while before either spiraling in or drifting away, depending on how it was launched. This is a rough, two-dimensional stand-in for what a massive object does to the actual four-dimensional fabric of space and time, and it captures something true about orbits, that planets are not being reeled in by an invisible line, but are coasting along a curve that the sun's mass has bent into existence around itself. The analogy has real limits. In the classroom version, friction from the fabric eventually drags the marble to a stop, spiraling all the way into the weight at the center. In the vacuum of real space, there is no friction to speak of, so planets that settle into a stable orbit can, in principle, continue circling for a very long time without losing energy the way the marble does. A separate, equally simple demonstration illustrates a related idea: the role that momentum and even the shape of a path play in motion under gravity. Picture two ramps of identical length side by side, both sloping down by the same overall amount. One is perfectly smooth and straight. The other has the same start and end height, but dips and rises along the way, an uneven, bumpy path rather than a straight one. Release identical balls down each ramp at exactly the same moment, and intuition tends to suggest they should arrive at the bottom together, since both traveled the same net drop in height. They do not. The ball on the uneven ramp reaches the bottom first because the early dip lets it accelerate more quickly than its counterpart on the straight ramp, building up momentum that carries it ahead, even as it later has to climb back up over the bumps. It is a small, almost playful reminder that motion under gravity depends not just on where you start and where you end up, but on the entire path in between, a lesson with echoes in far larger settings, from the winding orbits of comets to the paths light itself takes as it bends around massive objects on its way across the universe. Curvature explains orbits and time dilation well enough on its own, but general relativity carries one more consequence, arguably its strangest, tucked inside the mathematics almost as an afterthought. If mass curves the space around it, and that curvature moves along with the mass as it moves, then an object that accelerates in just the right way should be able to send ripples of that curvature outward, spreading through space the way ripples spread across the surface of a pond after a stone breaks its surface. These are gravitational waves, disturbances not in any medium like water or air, but in the geometry of space and time itself, stretching distances in one direction while squeezing them in the perpendicular direction as they pass, then relaxing back as the ripple moves on. Einstein predicted their existence not long after publishing General Relativity itself, working out the mathematics in 1916, but he was doubtful anyone would ever actually detect them. The effect, according to his own calculations, would be almost absurdly small for any event short of the most violent processes imaginable, and even then, the resulting distortion by the time it reached Earth would be a fraction of the width of a single atomic nucleus. It is easy to sympathize with his pessimism. For decades, most physicists treated gravitational waves as a mathematically interesting curiosity, real in principle, but hopeless to measure in practice. The instrument that eventually proved him only half right, in the sense that they are real, but not entirely undetectable, is called the Laser Interferometer Gravitational Wave Observatory, or LIGO, and it works on a deceptively simple principle borrowed from a 19th century optical technique. An interferometer splits a single beam of light into two, sends each half down a separate path, and then recombines them. If both paths are exactly the same length, the two halves of the beam recombine perfectly in step with each other, reinforcing one another. If one path becomes even very slightly longer or shorter than the other, the two halves fall out of step, and the combined light dims or shifts in a measurable, predictable way. It is a remarkably sensitive way to detect tiny changes in distance because light itself provides the ruler, and light's wavelength is extremely small and extremely consistent. LIGO consists of two nearly identical observatories, one in Hanford, in the state of Washington, and another roughly 3,000 kilometers away in Livingston, Louisiana. Having two widely separated detectors matters enormously, both because a genuine gravitational wave should register in both locations within a few milliseconds of each other, letting scientists rule out local sources of interference, such as a passing truck or a minor earthquake, and because comparing the tiny timing difference between the two sites helps triangulate roughly where in the sky a signal originated. At each site, a laser beam is split and sent down two perpendicular vacuum tunnels, each 4 kilometers long, arranged in an L shape. Mirrors at the far end of each tunnel bounce the light back, and in fact the beams are made to bounce back and forth roughly 300 times before finally recombining, effectively stretching the usable path length from 4 kilometers to well over 1,000 kilometers, folded into a much smaller physical footprint. If a gravitational wave passes through the detector, it stretches space very slightly along one tunnel while squeezing it along the other, changing the relative path length by an amount smaller than 1,000th the width of a single proton, and shifting the interference pattern of the recombined light in a way sensitive instruments can register. Achieving that level of sensitivity required extraordinary engineering. The mirrors themselves, each weighing about 40 kilograms, are among the smoothest human-made surfaces ever produced, suspended by threads of fused silica to isolate them from vibration. The tunnels are pumped down to a vacuum roughly 1/1,000,000th of ordinary atmospheric pressure, removing air molecules that would otherwise scatter the laser light and introduce noise. Even quantum mechanics itself becomes a practical obstacle at this scale, because the fundamental randomness in how individual photons behave introduces a kind of unavoidable static into the measurement. Engineers address this with a technique called light squeezing, which shifts that quantum uncertainty away from the specific property the interferometer is measuring and into a different property it largely ignores, reducing noise without violating the underlying laws of quantum mechanics, which cannot be eliminated, only redistributed. The result of decades of this kind of refinement is an instrument capable of detecting a change in distance smaller than 1 part in many trillions across a tunnel 4 kilometers long, an achievement that led 3 of the project's central figures, Rainer Weiss, Kip Thorne, and Barry Barish, to share the Nobel Prize in Physics in 2017 for their roles in conceiving, building, and realizing the observatory over more than 4 decades of work. The patience paid off on September 14, 2015, when LIGO recorded its first confirmed gravitational wave signal, later given the catalog name GW 150914. The pattern in the data, a rising chirp of frequency, followed by an abrupt cutoff, matched the theoretical signature of 2 black holes spiraling into one another and merging, one with roughly 29 times the mass of the Sun, and the other with roughly 36 times the mass of the Sun, colliding somewhere around 1.3 billion light-years away. In the final fraction of a second before merging, the two black holes released more power in gravitational waves alone than the combined light output of every star in the observable universe at that instant, a genuinely staggering figure that is difficult to hold in the mind for very long. And yet, by the time that wave had crossed the intervening distance and reached the detectors on Earth, it had weakened to the point of stretching each 4-kilometer detector arm by less than the width of a proton. The scale of the original event and the faintness of its eventual echo sit at almost opposite extremes, and both numbers are, in their own way, part of what makes the detection remarkable. That first detection turned out to be the beginning rather than an isolated event. A second confirmed signal arrived only a few months later, again from a black hole merger, this one roughly 1.4 billion light-years away. Over its first several years of operation, LIGO and its European counterpart, an observatory called Virgo, located near Pisa, Italy, together recorded upward of 80 confirmed black hole mergers, gradually building the first real, statistical picture of how common these events are and what range of masses tend to be involved. Then, in August of 2017, came a detection of a different character entirely, catalogued as GW170817, produced not by two black holes, but by two neutron stars, the extraordinarily dense collapsed remnants of massive stars, spiraling together and merging. What made this detection especially significant was that, unlike a black hole merger, a neutron-star collision was expected to produce ordinary light as well as gravitational waves, and it did. Within hours, roughly 70 observatories around the world using telescopes tuned to visible light, radio waves, X-rays, and gamma rays all identified the same event in the same patch of sky, confirming that the merger produced heavy elements through a process called rapid neutron capture, offering direct observational evidence for where much of the universe's gold, platinum, and other heavy elements actually come from. It marked the beginning of what astronomers now call multi-messenger astronomy, studying a single cosmic event through entirely different channels, gravitational and electromagnetic, at the same time, each one revealing details the other could not. LIGO has continued to be upgraded since those early runs, each round of improvements extending its sensitivity and the volume of space it can effectively listen to. A major upgrade completed in the early 2020s, which kept the observatories offline for roughly 3 years, introduced more reflective mirrors, improved mirror suspension systems, and a more refined form of quantum light squeezing, allowing the fourth major observing run to begin in May of 2023 with meaningfully improved sensitivity over earlier runs. That run also marked the first time LIGO operated alongside a new partner observatory, Kagra, located underground near Hida, Japan. Kagra holds the distinction of being both the first gravitational wave observatory built underground, which shields it from a great deal of surface vibration and seismic noise, and the first to cool its mirrors to extremely low temperatures, reducing thermal noise that would otherwise limit its precision. Further expansion is already underway or being planned. India is developing a fourth major detector, sometimes referred to as LIGO India, which will improve the triangulation of signal origins simply by adding another widely separated point on the globe from which to observe the same event. Later in the 2020s, an upgrade sometimes called LIGO Voyager is expected to introduce mirrors roughly 4 times heavier than the current ones, along with higher frequency lasers, both changes aimed at pushing sensitivity further still. Beyond that, lies a more ambitious, so far unbuilt proposal called Cosmic Explorer, envisioned as a pair of new observatories with arms considerably longer than LIGO's existing 4 kilometers, on the general principle that has held throughout this field's short history, that a larger interferometer is a more sensitive one. Perhaps the most striking proposal on the horizon is an entirely space-based observatory called the Laser Interferometer Space Antenna, or LISA, which would place 3 spacecraft in a triangular formation separated by roughly 2.5 million kilometers, using laser links between them in place of physical tunnels bounded by mirrors on Earth, removed from the vibration and seismic noise that limits ground-based detectors, and with arms vastly longer than anything buildable on the planet's surface. LISA would be sensitive to an entirely different range of gravitational wave frequencies than LIGO, including waves produced by the slow inspiral of supermassive black holes long before they get close enough to merge violently, sources far too faint and slow-moving for ground-based detectors to ever pick up. With a currently planned launch sometime in the mid-2030s, LISA remains more than a decade away, but its eventual data would open an entirely new window onto events that current instruments simply cannot see. LIGO and its ground-based relatives are remarkably sensitive instruments, but they are also, in an important sense, narrow ones. Gravitational waves, much like sound or light, can occur across an enormous range of frequencies, and a 4-kilometer interferometer built and tuned the way LIGO happens to be well suited to only a fairly high frequency slice of that range, the kind produced in the final, rapid moments before 2 black holes or 2 neutron stars collide, when they are whipping around each other hundreds of times per second. Slower, more gradual processes, like 2 much larger black holes orbiting each other from a wide distance, produce gravitational waves at a far lower frequency, and detecting those requires a completely different kind of instrument, one with an effective arm length not of kilometers, but of light years. Building a physical interferometer with arms that long is obviously impossible with current or even foreseeable technology, but astronomers found a clever workaround, using objects the universe had already provided, pulsars. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell, then a graduate student, who noticed an unusually regular pulsing radio signal in her observational data and initially only half-jokingly nicknamed it Little Green Men 1, before it was understood to be a natural phenomenon. A pulsar is the collapsed core of a massive star that has ended its life in a supernova, an object called a neutron star, spinning rapidly and emitting a narrow beam of radio waves from its magnetic poles, sweeping around like a lighthouse beam as the star rotates. From Earth, that beam registers as a regular pulse of radio energy each time it sweeps across us. Some pulsars, known as millisecond pulsars, spin so quickly and so stably that their pulses arrive with a regularity that rivals some atomic clocks, making them, in effect, natural cosmic timekeepers scattered across the galaxy at distances of thousands of light years. The idea behind what astronomers call a pulsar timing array is to use a carefully selected group of these millisecond pulsars spread across many different directions in the sky as the equivalent of mirrors at the far ends of an enormous, imaginary set of interferometer arms. Except instead of bouncing a beam of light sent from Earth, each pulsar generates its own signal, which simply needs to be received and timed with extreme precision using ordinary radio telescopes. If a low-frequency gravitational wave with a wavelength measured in tens of light years happens to pass between Earth and one of these pulsars, it will very slightly stretch or compress the space the pulsar's radio pulses travel through, causing those pulses to arrive at Earth a tiny bit earlier or later than a perfectly steady pulsar would otherwise suggest. Tracking a single pulsar's timing is not enough to prove anything on its own, since all sorts of mundane factors, from interstellar gas along the way to tiny irregularities in the pulsar's own rotation, can also shift the arrival time of its pulses. The key insight is that a genuine gravitational wave passing through the solar system should create a very specific pattern of correlated timing shifts across many different pulsars simultaneously, a pattern predicted mathematically in the 1980s by Ronald Hellings and George Downes, and now known as the Hellings-Downes curve, describing how strongly the timing shifts of two pulsars should agree with each other depending on how far apart those two pulsars appear in the sky. Random, unrelated noise would not produce this pattern. A shared gravitational wave washing over the whole solar system would. A collaboration called Nanograv spent more than 15 years carefully monitoring a set of 68 carefully chosen millisecond pulsars distributed across the sky and selected specifically for their timing stability, patiently building up enough data to search for exactly this kind of correlated pattern. On the 28th of June, 2023, the collaboration announced that their data showed a clear Hellings-Downes pattern, evidence for what is called a gravitational wave background, not a single sharp signal from one identifiable event the way LIGO detects black hole mergers, but a continuous, overlapping hum of extremely low-frequency gravitational waves washing over the solar system from countless sources at once, blending together the way individual voices blend into an indistinguishable murmur in a crowded room. The statistical confidence of the result stood at what physicists call the 3 sigma level, meaning there was roughly a 1 in 1,000 chance the pattern was simply a coincidence of noise. Physicists conventionally reserve the term discovery for results reaching the considerably higher 5 sigma threshold, but a 3 sigma result, especially one built from such a large and carefully controlled data set, is still regarded as strong evidence, and Nanograv and several partner collaborations around the world continue to gather additional years of data, specifically to push that confidence higher. What produces this background hum is thought to be, primarily, an enormous population of pairs of supermassive black holes, each pair sitting at the center of what were once 2 separate galaxies that have since merged into one. When 2 galaxies collide and merge, a process that unfolds over hundreds of millions of years, the stars within them mostly pass by one another harmlessly, since galaxies are so overwhelmingly empty that direct stellar collisions are rare, but the supermassive black holes at each galaxy's center do gradually sink toward the combined galaxy's new center under gravity's pull, eventually forming a bound pair that continues orbiting each other for a very long time, sometimes for longer than the age of the universe, allows them to fully spiral together and merge. Each of these slowly orbiting pairs, and there are expected to be a great many of them scattered across cosmic history, contributes a faint, steady gravitational wave, and the combined, overlapping contribution of countless such pairs, too numerous and too similar in frequency to pick apart individually with current techniques, is what pulsar timing arrays are detecting as a background rather than as distinct events. There is a second, more speculative reason this background is exciting to physicists, one that reaches back to the very beginning of the universe. For the first several 100,000 years after the Big Bang, the universe was filled with an extremely hot, dense plasma, a state of matter in which electrons and atomic nuclei move freely rather than bound together into neutral atoms. Light cannot travel far through a plasma without being repeatedly absorbed and re-emitted by charged particles, which means that no light produced before the universe cooled enough for neutral atoms to form, an event that occurred roughly 380,000 years after the Big Bang, can reach us directly. The oldest light astronomers can observe. The cosmic microwave background dates from the moment that fog finally cleared and represents an absolute wall beyond which no telescope built to detect light can ever see. Gravitational waves, however, are not made of light and are not slowed or absorbed by plasma at all, since they are ripples in space-time itself, rather than disturbances of any physical medium. In principle, primordial gravitational waves generated within the first fraction of a second after the Big Bang could still be crossing the universe today, having traveled essentially unimpeded the entire time, offering a theoretical window onto an era far earlier than the cosmic microwave background can ever reveal. Current pulsar timing data cannot yet isolate a signal this ancient from the louder foreground produced by merging supermassive black holes, but it represents one of the longer-term motivations driving the field forward, the tantalizing possibility of eventually hearing an echo of the universe's very first moments. It is worth stepping back further into history because the idea of an object so dense that light itself cannot escape it did not begin with Einstein at all, but with much older, more classical reasoning. In 1783, an English clergyman and scientist named John Michell, working entirely within Newton's older framework of gravity, calculated that a star packed densely enough would have an escape velocity, the speed needed to break free of its gravity entirely, exceeding the speed of light. Using Newton's equations alone, Michell reasoned that such an object would appear completely dark, since even light would be unable to leave its surface, and he referred to these hypothetical objects as dark stars. The French mathematician Pierre-Simon Laplace arrived at a similar conclusion independently a few years later. Neither had any way to know whether such objects actually existed, and the idea drifted into obscurity for well over a century, treated as an intriguing but purely theoretical curiosity, largely because nobody at the time understood what physical process could ever compress a star that densely in the first place. The modern version of the idea did not arrive until barely a year after Einstein published General Relativity, when the physicist Karl Schwarzschild, while serving in the German army during the First World War, worked out an exact mathematical solution to Einstein's equations describing the curvature of space around a perfectly spherical, non-rotating mass. Buried inside that solution was a specific radius, now called the Schwarzschild radius, at which the mathematics predicted that space and time would become so severely warped that nothing, not even light, could escape from within it. For decades, most physicists, Einstein among them for a time, treated this feature as a mathematical oddity unlikely to correspond to anything physically real, assuming nature would simply never compress matter that extremely. That assumption began to crumble in the 1930s when the astrophysicist Subrahmanyan Chandrasekhar calculated that a star's core, once it exhausts its nuclear fuel, can only support itself against its own gravity up to a certain mass, now called the Chandrasekhar limit, a little under 1.5 times the mass of the Sun. Below that limit, a dying star's core settles into a stable, extremely dense object called a white dwarf. Above it, nothing known at the time could stop the core from continuing to collapse. Chandrasekhar's early calculations were met with considerable resistance, including public skepticism from Arthur Eddington, one of the leading astrophysicists of the era, and notably, the same Eddington who had led the 1919 eclipse expedition, confirming general relativity in the first place. It took further decades of theoretical work, including calculations by Robert Oppenheimer and his colleagues in the late 1930s, describing what happens when a massive stellar core collapses without anything able to halt it. Before physicists broadly accepted that some stars really do collapse all the way down past any known stopping point, forming exactly the kind of object Schwarzschild's equations had described decades earlier. The physicist John Wheeler popularized the now familiar name for these objects, black hole, in a lecture in the late 1960s, and the term stuck, direct evidence that such objects genuinely exist in the universe rather than only in equations, took even longer to arrive. The first strong candidate, an X-ray source in the constellation Cygnus, called Cygnus X1, was identified in the early 1970s, its X-rays interpreted as the glow of superheated gas spiraling into an invisible companion object too massive and too compact to be anything else known to astrophysics. Confidence in its identity grew over subsequent decades as observational techniques improved, though it took until 1990 for its nature to be considered settled among most astronomers. In more recent years, evidence has grown dramatically stronger and more direct still. LIGO's detections of merging black holes provided compelling indirect confirmation of their existence through gravitational waves rather than light. Then, in 2019, an international collaboration called the Event Horizon Telescope, linking radio telescopes across the globe into a single enormous virtual instrument, released the first actual image of a black hole's shadow silhouetted against glowing surrounding gas for the supermassive black hole at the center of the distant galaxy M87. 3 years later, the same collaboration produced a similar image of Sagittarius A star, the considerably smaller supermassive black hole sitting at the very center of our own Milky Way galaxy, roughly 26,000 light-years from Earth, a concept born from an 18th century clergyman's paper calculations, dismissed for a century as a mathematical curiosity, had finally been not just inferred but, in a real sense, photographed. Long before LIGO ever recorded a direct gravitational wave, there was already strong indirect evidence that such waves must be real, and it came from an unrelated pair of pulsars discovered in 1974 by Russell Hulse and Joseph Taylor. The two pulsars, orbiting each other closely as a binary system, gave astronomers an unusually precise natural laboratory, since the regular radio pulses from one of them could be timed with extraordinary accuracy, revealing the shape and period of the pair's orbit in fine detail. General relativity predicts that a system like this, two extremely dense, rapidly orbiting objects, should slowly lose orbital energy over time by radiating it away as gravitational waves, causing the two stars to gradually spiral closer together and their orbital period to shorten in a very specific, calculable way. Hulse and Taylor tracked the pair's orbit for years and found that its period was indeed shrinking, and shrinking at a rate matching general relativity's prediction to within a small fraction of a percent. It was not a direct detection of a gravitational wave passing through a detector on Earth, but it was unambiguous evidence that the pulsars were losing energy in exactly the way emitting gravitational waves would require, earning Hulse and Taylor the 1993 Nobel Prize in Physics, and giving physicists decades of confidence, well before LIGO existed, that gravitational waves were real and not merely a mathematical abstraction. Other tests of general relativity have accumulated steadily across the 20th and 21st centuries, each closing off a slightly different way the theory could have been wrong. In the 1960s, the physicist Erwin Shapiro predicted that radio signals passing close to the Sun on their way between Earth and another planet should be very slightly delayed, not because they travel any slower, but because the curved space-time near the Sun lengthens the effective path the signal has to cross. Radar experiments bouncing signals off Venus and Mercury confirmed this so-called Shapiro delay to high precision, and the effect is now large enough and well understood enough that it, too, must be accounted for in the timing of deep space missions and, again, in positioning satellites. A more recent and considerably more expensive test came from a dedicated satellite called Gravity Probe B, launched in 2004, carrying 4 of the roundest objects ever manufactured, gyroscopes machined into nearly perfect spheres and cooled to extremely low temperatures to eliminate any friction that might disturb their spin. General relativity predicts 2 subtle effects on an orbiting gyroscope's axis of spin. One, called the geodetic effect, arises simply from the gyroscope moving through the curved space-time around the Earth. The other, a considerably smaller effect called frame dragging, arises from the Earth's own rotation, very slightly twisting the surrounding space-time along with it, an effect general relativity predicts for any rotating mass. After years of painstaking data analysis, both effects were confirmed. The geodetic effect to within about 1% of its predicted value, and the frame dragging effect, roughly 170 times smaller and correspondingly harder to measure, to within about 20%, a testament to just how demanding these experiments are, even when the underlying prediction has already been well established by other means. Gravitational lensing, the same bending of light that Eddington's eclipse expedition first confirmed in 1919, has itself grown from a delicate one-time demonstration into one of astronomy's standard everyday tools. Massive galaxy clusters bend and distort the light of far more distant galaxies sitting directly behind them, sometimes smearing that light into long arcs, or even splitting a single distant galaxy's image into several duplicated copies arranged symmetrically around the foreground cluster. Because the amount of bending depends on how much mass sits in the foreground, including mass that emits no light at all, astronomers use these lensing patterns as a direct way to map the distribution of dark matter in galaxy clusters, entirely independent of the rotation curve method pioneered decades earlier. A related and considerably more delicate version of the same effect, called microlensing, occurs when a single, relatively small object, sometimes even an individual star or a planet orbiting it, passes directly in front of a much more distant background star from Earth's point of view, very briefly and precisely brightening the background star's light as the foreground object's gravity focuses it like a lens. This technique has become one of several productive methods for discovering exoplanets, including some too small or too distant to detect through other means, an application Einstein himself, when asked about the idea in the 1930s, considered interesting but doubted would ever be practically useful, since he assumed the alignments required would be too rare to ever observe in practice. Modern wide-field sky surveys, patiently watching millions of stars simultaneously, have proven that doubt wrong many times over. It is worth returning for a moment to the missing mass that kept surfacing throughout the story of our galaxy's motion toward the Great Attractor and the Shapley supercluster, because that gap between visible matter and the gravity actually observed is one of the longest-running open puzzles in modern astronomy. Predating even the Great Attractor by decades, the first hint came in 1933, when the astronomer Fritz Zwicky studied the motions of galaxies within the Coma cluster and found they were moving far too quickly relative to one another to remain gravitationally bound together, given only the visible mass of the stars he could see. By his calculations, the cluster needed several hundred times more mass than was visible in order for its gravity to hold such fast-moving galaxies together at all. Zwicky proposed that some form of unseen matter, which he called dunkle Materie, dark matter in his native German, must be filling in the difference. But the idea attracted little serious attention for decades, partly because Zwicky's abrasive reputation among colleagues did him no favors, and partly because the observational tools of the time simply were not good enough to investigate the claim more rigorously. The idea returned to the center of astrophysics in the 1970s, largely through the careful, painstaking work of the astronomer Vera Rubin, working alongside Kent Ford, measuring how quickly stars orbit at different distances from the centers of spiral galaxies. Newton's gravity, applied to the visible distribution of stars in a galaxy, predicts that stars far from the center should orbit noticeably more slowly than stars closer in, the same way outer planets in our solar system orbit the sun more slowly than inner ones. Rubin and Ford found, across galaxy after galaxy, that this simply was not happening. Stars far out at the edges of these galaxies were orbiting just as quickly as stars much closer to the center, a flat rotation curve rather than the declining 1 Newtonian gravity applied to only the visible matter would predict. The most straightforward explanation, then as now, is that each galaxy is embedded in a much larger, invisible halo of matter, extending well beyond the visible disk of stars, providing the additional gravity needed to keep those outer stars moving as quickly as they do. Further, independent evidence accumulated over the following decades from multiple directions at once, each pointing toward the same conclusion through a completely different method. Detailed studies of the cosmic microwave background reveal subtle patterns that depend sensitively on how much total matter, visible and invisible, existed in the early universe, and those patterns consistently indicate several times more matter than can be accounted for by ordinary light-emitting material alone. Perhaps the most visually striking piece of evidence came from a system astronomers call the Bullet Cluster, 2 galaxy clusters that collided with one another and are now passing through each other. Observations in X-ray light reveal where the hot, ordinary gas from both clusters has piled up and slowed down due to friction during the collision, while gravitational lensing observations reveal where most of the mass actually sits, and the 2 locations do not match. The bulk of each cluster's gravitational mass sailed straight through the collision, largely undisturbed, offset from the ordinary gas that collided and slowed, exactly as expected if that mass consists of some form of matter that barely interacts with anything except through gravity itself, passing through the collision the way ghosts might pass through walls. What that matter actually is remains genuinely unresolved. Leading candidates for decades have included weakly interacting massive particles, sometimes called WIMPs, a hypothetical class of particle that would interact with ordinary matter only very rarely, and axions, an entirely different and considerably lighter hypothetical particle originally proposed to solve an unrelated puzzle in particle physics. Enormous, extremely sensitive underground detectors, shielded deep beneath mountains or old mines, specifically to block out cosmic rays and other interference, have spent decades searching for the rare, faint signal a dark matter particle might leave behind if it happened to collide with an ordinary atomic nucleus, and so far, none has been conclusively detected. It remains entirely possible that dark matter consists of some particle not yet included in any current theory, or, less popular among physicists, but not entirely dismissed, that gravity itself behaves slightly differently than Einstein's equations predict at the enormous distance scales involved in galaxies, removing the need for unseen matter altogether. The evidence from the bullet cluster and several other independent lines of observation makes this second option considerably harder to sustain than it once was, since a modification to gravity alone struggles to explain why mass and ordinary matter would end up so cleanly separated during a collision. But the debate has not been entirely settled, and dark matter remains, quite literally, one of the largest gaps in humanity's understanding of what the universe is actually made of. All of this, the bending of starlight, the correction of satellite clocks, the ripples LIGO detects, the flow of galaxies toward the great attractor, rests on general relativity working extremely well, and it does work extremely well, across an enormous range of situations, from the gentle curvature around the Earth to the extreme curvature around merging black holes. But physicists generally regard it as an incomplete theory rather than a final one, and the reason brings us back to the singularity mentioned earlier, the point where the mathematics describing the very center of a black hole simply stops making sense. The trouble is that general relativity describes gravity as smooth, continuous curvature, while the other three fundamental forces of nature, electromagnetism, and the two forces that operate inside atomic nuclei, are all described by quantum mechanics, a framework built instead around discrete packets of energy and inherent probabilistic uncertainty at small scales. These two frameworks, general relativity and quantum mechanics, have each been tested to extraordinary precision within their own domains, and yet nobody has managed to combine them into a single, mutually consistent description of gravity that also behaves quantum mechanically at very small scales. This becomes an urgent practical problem rather than a purely academic one in exactly two places, at the singularity inside a black hole, where an enormous amount of mass is compressed into a vanishingly small region, and in the first unimaginably brief fraction of a second after the Big Bang, when the entire observable universe is thought to have been compressed into a region small enough that quantum effects should have mattered a great deal. In both cases, general relativity alone predicts an outcome, infinite density, that most physicists suspect is really a sign the theory has been pushed past the point where it can still be trusted, rather than a genuine feature of reality. One particularly sharp version of this tension emerged from the work of Stephen Hawking in the 1970s, when he applied quantum mechanical reasoning to the region just outside a black hole's event horizon and found that black holes should not be perfectly, eternally black after all. Quantum fluctuations near the horizon, he argued, should allow black holes to very slowly radiate particles and energy outward, a process now called Hawking radiation, causing a black hole to gradually lose mass and, over an extraordinarily long time scale, eventually evaporate away entirely, For any black hole of a realistic astrophysical size, this process is so slow that it is utterly negligible on any timescale relevant to human observation, far slower even than the current age of the universe. So nobody expects to observe it directly anytime soon. But the theoretical implications proved deeply unsettling. If a black hole eventually evaporates completely, what happens to all the information about whatever fell into it over its lifetime? Every detail about the matter that originally formed it and everything it later consumed? Quantum mechanics insists that information cannot simply be destroyed, yet Hawking's original calculation suggested that the radiation coming back out would be purely random, carrying no trace of what had gone in. This puzzle, known as the black hole information paradox, has occupied theoretical physicists for decades, and while various proposed resolutions exist, including subtle ideas about how information might be encoded on a black hole's horizon rather than genuinely lost, no single resolution commands universal agreement. Attempts to build a complete theory that folds gravity into the quantum framework, generally grouped under the label of quantum gravity, have followed several different paths without arriving at a settled destination. String theory, developed extensively from the 1970s onward, proposes that the fundamental constituents of nature are not point-like particles at all, but extremely small vibrating strings, with different vibration patterns corresponding to different particles, including, in versions of the theory that include gravity, a particle responsible for carrying the gravitational force itself. An entirely separate approach, loop quantum gravity, developed largely from the 1980s onward, instead attempts to directly quantize space-time itself, proposing that space, at its smallest scale, is not smooth and continuous, but built from discrete, interconnected loops, somewhat the way a smooth-looking fabric is, on close enough inspection, made of individual threads. Both frameworks are mathematically sophisticated, and each has attracted dedicated communities of researchers over multiple decades, and each has produced genuine theoretical insight, but neither has yet produced a testable prediction that current or near-future instruments could actually check, which is an honest and somewhat frustrating place for the field to still find itself in, nearly a century after the tension between general relativity and quantum mechanics first became apparent. It remains one of the most fundamental open questions left in physics, sitting quietly underneath every gravitational wave chirp, LIGO records, and every satellite clock correction made in orbit. There is another thread worth pulling on here, because the same Edwin Hubble, who first proved that other galaxies exist beyond the Milky Way, went on, only a few years later, to make an even larger discovery about how those galaxies behave. Working through the 1920s, with measurements of galaxy distances and their light's redshift, meaning how much the wavelength of a galaxy's light had been stretched toward the red end of the spectrum on its way to us, Hubble noticed a striking pattern. Nearly every galaxy he measured was moving away from us, and more distant galaxies were moving away faster than nearer ones, in a roughly consistent proportion. The straightforward and, at the time, startling interpretation was that space itself is expanding, carrying galaxies apart from one another, the way dots painted on the surface of an inflating balloon spread apart as the balloon grows, without any of the dots actually moving across the balloon's surface on their own. This relationship, now called Hubble's law, provided some of the earliest strong evidence for what is now called the Big Bang model, the idea that the universe began in an extremely hot, dense state and has been expanding and cooling ever since. For most of the 20th century, the open question surrounding this expansion was not whether it was happening, but whether it was slowing down. Gravity, after all, pulls everything together, so most cosmologists reasonably expected the mutual gravitational attraction between all the matter in the universe to gradually decelerate the expansion over time, with the only remaining question being whether there was enough total matter for gravity to eventually halt the expansion entirely and pull everything back together, or too little, leaving the expansion to coast onward forever at an ever-slowing pace. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and another led by Brian Schmidt and Adam Rees, set out to measure exactly this deceleration by carefully tracking a particular kind of exploding star called a Type 1, a supernova, whose peak brightness is remarkably consistent and predictable, making them useful as reliable distance markers across billions of light years. Both teams, working independently and expecting to measure how much the expansion was slowing, instead found the opposite. Distant supernovae appeared fainter and therefore farther away than they should have been if the expansion were merely coasting or slowing under gravity's pull. The expansion of the universe was not decelerating at all. It was speeding up. This result was unexpected enough that both teams spent considerable time trying to rule out more mundane explanations, intervening dust dimming the light, unusual properties in more distant supernova, calibration errors, before accepting that the acceleration itself was real. The explanation cosmologists settled on requires proposing an entirely new ingredient in the universe's energy budget, an invisible, uniformly distributed component now called dark energy, which behaves unlike ordinary matter or radiation in that its effect grows relatively stronger rather than weaker as the universe expands and dilutes everything else. Current measurements suggest dark energy makes up roughly 68% of the total energy content of the universe, with the remaining matter, both ordinary and dark, making up most of what is left. Despite that dominant share, almost nothing is known about what dark energy actually is at a fundamental level, beyond the fact that its effects can be measured and its overall behavior matches, reasonably well, a simple mathematical term Einstein himself had originally added to his equations decades earlier and later removed, a constant value assigned to empty space itself, sometimes called the cosmological constant. Whether dark energy really is exactly that constant, or something more complex that merely resembles it at the precision current instruments can achieve, remains an active and genuinely unresolved question, with entire dedicated space telescopes and ground surveys currently underway, specifically to measure whether its strength has changed at all over cosmic history. This deep connection between gravity and expansion loops directly back to the voids and superclusters described earlier. In regions dense with galaxies, ordinary gravitational attraction between all that matter works against the underlying expansion, slowing it locally, which is part of why the concentrated mass in Laniakea and the Great Attractor can pull our galaxy toward them, despite the overall expansion of the universe pulling everything apart at the same time. In an empty void, with far less matter present to resist it, the same underlying expansion proceeds with comparatively little opposition, allowing voids to grow proportionally faster than the denser regions around them. Precisely the mechanism described earlier as part of why the dipole repeller appears to push nearby galaxies away, even without dark energy specifically added to the explanation. Add dark energy's accelerating effect on top of that baseline expansion, and the contrast between crowded superclusters and empty voids becomes even more pronounced over the universe's history, gently sculpting the cosmic web into sharper relief the longer the universe continues to age. It is worth circling back, gently, to the nature of time itself, since that is where this all began, with a satellite quietly correcting its own clock. Gravitational time dilation is only part of a larger, stranger picture that falls out of relativity, one that concerns not just how fast time passes for someone, but whether there is even a single, universal answer to the question of what is happening right now, somewhere else in the universe. In relativity, space and time are woven together into a single four-dimensional structure, usually just called space-time, rather than treated as two entirely separate things, an unchanging three-dimensional stage with a separate, universal clock ticking the same way for everyone watching the play unfold on it. One of the stranger consequences of this merger, discovered by Einstein even before general relativity in his earlier 1905 theory of special relativity, is that two observers moving at different speeds relative to each other can genuinely disagree about whether two distant events happened at the same time or not, and neither observer is more correct than the other. This is not a matter of one of them being confused or receiving delayed information. Two carefully synchronized clocks, compared by two observers in relative motion, will show those observers disagreeing about simultaneity itself, a result confirmed as thoroughly as any other prediction of relativity. There is no single universal present moment shared across the whole universe, no cosmic clock ticking the same beat for everyone everywhere. Each observer effectively carries their own slice through space-time, their own definition of now, and different observers moving differently slice it at slightly different angles. This has led some physicists and philosophers of physics to describe the universe as a kind of block, a four-dimensional structure in which every moment, past, present, and future, exists as a fixed, equally real part of that structure, with our felt sense of time flowing forward from past to future being something closer to a feature of human consciousness moving through the block rather than a feature fundamentally built into space-time itself. This interpretation, often called the block universe view, is not universally agreed upon, and other physicists and philosophers argue for alternative readings of the same mathematics that preserve a more meaningful, physically real distinction between past, present, and future, sometimes called presentist or growing block interpretations. What is not disputed is the underlying physics, the relativity of simultaneity, and the genuine warping of time by both speed and gravity. It is only the deeper philosophical question of what that physics actually implies about the fundamental nature of time and change that remains open, an area where physics runs directly into unresolved questions in philosophy rather than providing a clean, settled answer on its own. Gravitational time dilation folds neatly into this same picture, since it, too, is really a statement about space-time's shape, rather than time behaving like a separate, independently ticking clock. A person deep in a gravitational well is not experiencing a different flow of time in some active sense from their own point of view. Locally, their time always feels perfectly ordinary to them, ticking at the same 1 second per second it always has. It is only when their clock is compared against a clock somewhere else, somewhere with different curvature, that any difference shows up at all, an observation that depends entirely on the relationship between the two locations, rather than on any absolute property belonging to either one alone. In that sense, both special and general relativity point toward the same underlying lesson, one that took physicists the the better part of a century to fully absorb. Time is not a single, universal river flowing at the same rate everywhere for everyone. It is a local, relative quantity shaped by both motion and gravity, differing subtly from place to place and observer to observer in ways too small to notice in ordinary daily life, but large enough at the extremes to slow a falling astronaut's breathing to an apparent standstill when viewed from a safe distance, or to stretch a supernova's light by billions of years on its way across an expanding universe. Returning to the cosmic web itself, the dipole repeller is far from the only void astronomers have identified, and studying voids in general has become its own quietly productive corner of cosmology. One of the more famous examples, called the Bootes void, was discovered in the early 1980s and spans roughly 330 million light-years across, making it, at the time of its discovery, one of the largest, apparently empty regions ever found, containing only a small handful of galaxies scattered through a volume where hundreds might otherwise be expected. For a while, it was informally nicknamed the Great Nothing, and its discovery helped cement the broader realization that the universe's large-scale structure genuinely does include such enormous, sparsely populated regions. Rather than being an artifact of limited early survey data, large-scale surveys conducted since then, mapping the positions of hundreds of thousands or even millions of galaxies across wide swaths of sky, have filled in an increasingly detailed picture of the cosmic web's overall shape. One especially large filamentary structure identified within the Sloan Digital Sky Survey data, sometimes called the Sloan Great Wall, stretches for well over 1 billion light-years, standing as one of the largest coherent structures identified in the observable universe, threading between voids the way a single long strand might weave through an enormous, loosely woven net. Structures on this scale raise their own quiet puzzle, since a small number of extremely large structures identified in various surveys have prompted some cosmologists to ask whether the universe's structure is fully consistent at every scale with the standard cosmological model's assumption that matter is distributed roughly uniformly once you average over sufficiently large volumes. So far, the standard picture has held up under scrutiny each time it has been tested more carefully, but the largest known structures remain an area cosmologists continue to study specifically to make sure nothing about the basic assumption is being overlooked. The overall pattern of filaments and voids is not random either, and one particularly elegant piece of evidence for this comes from a subtle feature called baryon acoustic oscillations, a faint but measurable preference for galaxies to be separated from one another by one particular characteristic distance, more often than by other distances. When averaged across enormous numbers of galaxy pairs, this preferred distance traces back to sound-like pressure waves rippling through the hot plasma of the very early universe, the same era discussed earlier in connection with the cosmic microwave background before neutral atoms had even formed. Those ancient pressure waves left a faint imprint on where matter eventually clumped together as the universe cooled and expanded, an imprint that has grown alongside the universe's overall expansion, but remains detectable today as a subtle statistical pattern in how galaxies are spaced relative to one another. Detecting this pattern gives cosmologists an independent, largely gravity-free method for measuring the universe's expansion history, a helpful cross-check alongside the supernova measurements that first revealed the universe's accelerating expansion, and the two methods have generally reinforced each other's conclusions. lending confidence to the overall picture, even as questions like the precise nature of dark energy remain unresolved. Some of the future instruments mentioned earlier are further along than they might sound. Before committing to building the full 3 spacecraft LISA mission, the European Space Agency launched a single smaller precursor mission called LISA Pathfinder in 2015, carrying 2 small test masses inside a single spacecraft and using an onboard laser system to measure their relative position with extraordinary precision, checking whether the technology needed for the full mission, isolating a floating test mass from every disturbance except gravity itself, could actually work as well as engineers hoped. The mission exceeded its own targets, demonstrating a level of measurement precision better than originally required, and giving the agency enough confidence to move forward with formally developing the full 3 spacecraft version of LISA, now planned for launch in the mid-2030s. It is a useful reminder that projects like this rarely leap straight from proposal to finished observatory, but instead advance through smaller demonstrations that quietly retire the biggest technical risks well before the final, much larger and more expensive instrument is ever built. The Event Horizon Telescope collaboration, too, has continued expanding since its first black hole images. Additional radio telescopes have joined the network in the years since the original images of M87 and Sagittarius A star, improving the resolution and reliability of future images. And researchers have discussed eventually adding a telescope in space to the network, which would extend the effective size of the virtual instrument well beyond what is possible using only observatories fixed to the surface of the Earth. Future goals for the collaboration include capturing actual video rather than a single static image of the swirling gas around a black hole shadow, which would let astronomers directly watch how that gas moves and evolves over time, rather than seeing only a single frozen snapshot, and potentially testing general relativity's predictions about a black hole's shape and behavior with even greater precision than the original images allowed. Meanwhile, the pulsar timing array collaborations, including Nanograv, along with partner projects in Europe, India, China, and Australia studying the same background hum using their own sets of pulsars, continue adding years of additional data to their data sets, specifically working to push their confidence in the gravitational wave background result past the 3 sigma level reported in 2023 and toward the considerably more stringent 5 sigma threshold. Physicists reserve for a firm discovery, combining data across these independent collaborations into a single global effort, an approach sometimes called the International Pulsar Timing Array, offers a faster path to that higher confidence than any single collaboration working alone could achieve, since it multiplies the number of pulsars and years of data available for the underlying statistical analysis. Beyond simply firming up the existing signal, researchers hope that enough additional data will eventually let them separate out contributions from especially close or especially massive individual supermassive black hole binaries from the general background hum, effectively picking out individual voices within what currently sounds like an undifferentiated murmur, and perhaps, much further down the line, catching a first genuine glimpse of the far older, far fainter primordial, gravitational waves that may still be crossing the universe from its very first moments. There is a pleasingly down-to-earth postscript to all of this, one that brings the story back from galaxies and black holes to something almost within arm's reach. For most of the 20th century, Gravitational time dilation was something that needed either an atomic clock flown around the world on an airliner, or a beam of gamma rays sent down a tall tower, or an entire constellation of orbiting satellites to detect at all. Ordinary differences in height, the kind separating a ground floor room from the one just above it, produced changes in the flow of time far too small for any instrument of the time to notice. That stopped being strictly true sometime in the 2010s, once physicists developed a new generation of atomic clocks called optical lattice clocks, which trap and measure the vibrations of individual atoms using visible light rather than the microwave frequencies older atomic clocks relied on, reaching a precision so extreme that two such clocks, run side by side under identical conditions, would not be expected to drift apart by so much as a single second, even if left running for a span of time longer than the current age of the universe. At that level of precision, gravitational time dilation stops being an exotic effect reserved for satellites and black holes and becomes something measurable across an ordinary laboratory tabletop. In a series of experiments carried out primarily at the National Institute of Standards and Technology in the United States, physicists placed one optical lattice clock roughly 33 centimeters, not much more than the height of a large dinner plate, stood on its edge, higher than an identical clock sitting beside it, and measured a small but genuine difference in how quickly time passed between the two, matching the tiny effect predicted by general relativity for that modest difference in height above the Earth's surface. Later refinements using clouds of ultra-cold atoms held in a single lattice clock pushed the demonstrated height difference down further still, eventually to a matter of just a few millimeters, edging toward a level of precision that could, in principle, let scientists compare the relative height of two distant locations simply by comparing how quickly their clocks tick relative to one another. An emerging technique, sometimes called relativistic geodesy or chronometric leveling, it raises a quietly strange, almost domestic possibility that measuring which of two shelves in a room sits very slightly closer to the center of the Earth might someday be done not with a tape measure or a surveyor's level, but by listening patiently to two clocks slowly, almost imperceptibly disagreeing with each other. Taken all together, gravity turns out to be a strange kind of thread running through almost every scale of the universe at once. It is the reason a satellite's onboard clock needs a small daily correction, the reason Mercury's orbit drifts in a way Newton's older equations could never quite explain, the reason an astronaut skimming close to a black hole and returning could find centuries had passed for everyone left behind, and the reason our entire galaxy drifts steadily toward one region of the sky while seeming to be pushed away from another that, as far as anyone can tell, is essentially empty. The same curved geometry explains all of it at every scale, from a laboratory tower in Massachusetts to a supercluster of galaxies 250 million light-years away. And yet, for a theory that has passed every experimental test thrown at it for more than a century, general relativity leaves behind a substantial list of things nobody yet fully understands. What actually happens at the singularity inside a black hole remains unknown, since the theory's own mathematics breaks down exactly at the point where an answer would be most interesting. What dark matter is made of, despite decades of increasingly sensitive searches, remains unknown, with underground detectors around the world still watching quietly for a signal that has not yet arrived. What dark energy actually is, beyond a name and a measured overall strength, remains unknown, and current current and near-future telescopes are specifically designed to determine whether its strength has changed at all across cosmic history, a measurement that could either quietly confirm the simplest existing model or force a considerably more interesting revision of it. Whether the dipole repeller is a genuine, confirmed feature of the local universe or an intriguing hypothesis still awaiting firmer confirmation remains, for now, an open question that better surveys of the zone of avoidance should eventually help settle, and how to unite general relativity with quantum mechanics into a single, coherent description of nature, resolving tensions that show up most sharply inside black holes, and in the earliest instance after the Big Bang, remains perhaps the deepest open problem in all of theoretical physics. With multiple serious proposed frameworks and, so far, no experimental way to distinguish decisively between them, none of this uncertainty is a weakness in the science. It is closer to the opposite, a sign of exactly where the genuinely interesting work is still happening. Detectors are being built right now that did not exist even a decade ago. Pulsar timing collaborations around the world are quietly adding more years of data to their datasets every single day, inching toward a firmer answer about the gravitational wave background and what, precisely, it is made of. The laser interferometer space antenna is moving steadily from a successfully tested concept toward an actual mission, still more than a decade from launch, but no longer merely theoretical. The Event Horizon Telescope continues to grow, telescope by telescope, toward the goal of watching a black hole's shadow shift and change over time rather than seeing only a single still frame. Underground laboratories continue their long, patient watch for a dark matter particle that may or may not ever announce itself. Wide-field sky surveys continue mapping the positions and motions of millions upon millions of galaxies, filling in the shape of the cosmic web in ever finer detail and refining our understanding of exactly how our own galaxy is being carried along within it. It is worth sitting for a moment with how much of this rests on ideas that once sounded almost too strange to take seriously. A clergyman doing arithmetic by hand in the 1780s, wondering whether a star could be so dense that light could never leave it. A patent clerk turned physicist working through the consequences of a simple thought experiment about a windowless, accelerating room. A pair of astronomers in the 1970s patiently timing the radio pulses from a distant, spinning stellar corpse for years on end, watching its orbit slowly shrink exactly as an untested theory said it should. Each of these, taken on its own, might have remained a curiosity, an elegant piece of mathematics with no clear connection to anything measurable. Together, tested against each other and against nature over more than a century, they have built into something remarkably solid, a description of gravity good enough to guide spacecraft across the solar system, precise enough to correct the clock in a phone resting quietly on a nightstand, and expansive enough to describe the slow, patient drift of galaxies across hundreds of millions of light years, all while still leaving enough unanswered right at its edges to keep entire fields of physics occupied for decades yet to come. That, in the end, is a reasonable place to leave it for tonight. Gravity is not simply a force pulling objects together the way it might have seemed from the ordinary experience of things falling. It is the shape of space and time itself, bending gently around every mass in the universe, slowing clocks, guiding orbits, carrying galaxies along invisible currents, and rippling outward whenever something massive enough moves in just the right way. It is, at once, one of the most thoroughly tested ideas in all of science, and one that still leaves some of the deepest questions about the universe genuinely, patiently open, waiting for whichever quiet, careful measurement comes next.